All right, howdy class. So today we're going to wrap up our discussion of phase transitions. And we're going to do that by, again, discussing this very peculiar point, this point here, the end of the liquid vapor phase transition line. Which we denote as a critical point. Now, as we started discussing last lecture, that point is very peculiar. It demarks the end of a sequence of points in the temperature pressure plane, these points along this line here, where a system with those parameters being controlled, temperature and pressure being controlled, below the critical point abruptly changes from one form of matter, say a liquid, to another, the vapor. At that point, beyond that point at least, that transition between liquid and vapor is smoothed out. They're indistinguishable phases. I can smoothly convert between one and the other. Exactly at that critical point, there's something in between the system being distinguishable, being able to label liquid-like and vapor-like phases, from indistinguishable, being able to interconvert between those two smoothly. The critical point is a singular point at which the system is somewhere in between those two extremes. We started making some sense of that point by thinking about the phase diagram in the temperature density plane, which is convenient because we know that density is a good order parameter for the liquid vapor phase transition. Again, over at low density, we have a vapor. At high density, we have a liquid. Underneath this curve is a region of coexistence. That coexistence curve ends at a point, that critical point, which has a location in the density temperature plane. We'll denote rho C and TC. Viewed in this light, it becomes clear that that point, what's special about that point is it really indicates where the distinction in density between the liquid and the vapor goes away. Associated with that smooth conversion between liquid and vapor is some real universal behavior. And we quantified that last lecture. We noted that experimentally, if you were to measure how the density changes relative to its critical density as a function of temperature, less than its critical temperature, that for any molecular fluid, the density dependence goes like a power law with some fractional power, turns out to be 0.327. That's true for water, that's true for methanol and argon. Any molecular fluid that supports liquid and vapor phases, which are essentially all molecular fluids, will have this universal coexistence curve. And in fact, we noted that that sort of behavior, that universality associated with the coexistence curve, was true not only for molecular fluids, it was exactly the same for mixtures, say water and oil, for magnetization, surprisingly, how your fidget spinner loses its magnetic moment as a function of temperature, goes away in the exact same form as a liquid turns into its vapor near its critical point. And we introduced simple models known as the lattice gas or the Ising model, which when solved numerically exactly, say on a computer, gave the exact same scaling behavior as what's observed experimentally. So this universality tells you that there are some truly universal, unifying features to critical points, to systems approaching their critical point, which is really very independent of molecular details. It's true for a whole host of seemingly disparate transitions. And that actually motivated us to then introduce this lattice gas, or the Ising model, as a kind of minimal model that we could actually make some sense out of this transition with. So naively, one might have expected that in order to say something about a critical point, one needed to provide lots of molecular detail. This universality tells us that's not true. And so it is sufficient to write down what is such a simple model for such a complex and interesting behavior. So essentially what we're going to do all class is remind ourselves of what that model is, what the lattice gas model is, remind ourselves why it's hard to kind of study analytically, and play around more with those simulations we introduced at the end of last lecture, saying that, well, it's a model, we can study that model on a computer, and we can try to gain some insight into the molecular behavior, the microscopic behavior underlying critical points by studying that model. Okay, so let's remind ourselves of what the lattice gas was. So the lattice gas, imagine that I could think of a liquid vapor phase transition by putting molecules or gridding up space on a lattice, imagining that locally each one of those grids, each one of those cells is about a little larger than a molecule. Such that any one of those cells is only likely to have one or no molecules in it. And I could color the cells that have a molecule in it, say with this blue color. Maybe those cells have particles in it in this configuration. Maybe that one does as well. And maybe this one here does. And I can label the dynamical state of this system with variables that tell me whether or not a molecule is in any one of those cells. For example, this cell here, there are no molecules in that cell. So I would say that it is vapor-like. And I have a number, say for cell I, denoted Ni, which, if that cell is unoccupied, returns 0. That's to be contrasted with that cell, which has a molecule in it, locally liquid-like. And if I call that cell J, then Nj returns 1, saying that that cell is filled. Now, in addition to those binary variables, we have a model for what the interactions between cells are like. And if we imagine that in each cell there is a molecule and those molecules interact, it's those attractions which stabilize the liquid state, then I can imagine that neighboring cells that are both filled with molecules have some favorable attraction that will denote minus epsilon, such that the energy can be written as minus epsilon times the sum of how many nearest neighbor cells are both liquids. And a way to denote that both of them are liquids is to multiply those indicator functions, those binary variables, together. If both of them are 1, meaning both of them are liquid-like, that returns 1 overall. I have that favorable energy. If either of them are 0, then I'll get no favorable energy. And the sum is over pairs I and J that are neighbors. And in this sort of square lattice I'm showing in 2 dimensions, there are 4 nearest neighbors. 1 to the right, 1 to the left, 1 up, and 1 down. We remarked that this system is slightly different than the kinds of systems we've studied previously, in that both the energy can change, as well as the number of particles. By changing the occupancy of one of the cells, I'm changing the number of particles, because the number of particles is just a sum over those number of cells. Let's say we have m cells. And in such a case, if both n and energy can fluctuate, then the probability of observing a microstate of the system is proportional to that usual Boltzmann factor, which tells us about energy fluctuations, and now a factor associated with the changing particle number of the system multiplied by beta mu, which is telling you about the entropy change in the bath associated with moving some number of particles from the bath into the system. Now, these interactions that are specified here, make studying this system analytically really hard. The reason for that is if I wanted to know the probability of cell I being occupied relative to cell I being unoccupied, well, this probability of a microstate tells me that it has a piece that has to do with e to the beta mu n nu 1 minus n nu 0 gives me overall beta mu 1. But in addition to that piece, 1 minus 0, I have a piece that depends on e to the beta epsilon, the number of liquid neighbors for that cell I. Which means that the probability of observing a particular cell I in a particular state, filled or unfilled, depends on what the states of the other cells are. So we would say that the statistics of cell Ni depend on the other n's, or using statistical language, we would say that the state of cell I is correlated with the states of cells J. Those correlations break the sorts of structures we've used to solve for things like partition functions previously, where particles were independent. Particles are independent. Partition functions factorize the probabilities of seeing a particle in a specific state is independent, so it factorizes, which lets us solve a single particle problem and turn that solution into a many particle problem, because it's just n factors of that single particle, say partition function. When the cells are correlated, we can't use that trick anymore. But we in fact noticed that you had to have correlations. That's the only way to have that heat capacity diverge. The only way to get infinite fluctuations is to have infinite ranged correlations. We introduced kind of heuristically this mean field theory that I think was useful for you to see, but again is too complicated to really worry too much about the details. It's more just a proof of an existence proof that such techniques could be used, which you can go learn about in more advanced classes. Sufficient for our case is to note that this model can be solved numerically. And if one does that, say by learning how to do it in Chem 195, which for those juniors or underclassmen in the class could imagine taking that in spring of 2021. There's a whole class devoted to algorithms for studying things like phase transitions. If one could study this numerically, you would find that in 2D, if I looked at the average occupancy less that its critical value, which for this system is just a half, that indeed goes like T minus Tc to some power, but in 2 dimensions, that power is not 0.327, but 1/8. However, this is the critical exponent, that 1/8, the critical behavior seen in 2-dimensional systems like lipid bilayers. If you solve this lattice gas model numerically in 3D, and you measure the average density less that 1/2 as a function of temperature relative to its critical temperature, what one finds is indeed the exact answer one sees experimentally. Demonstrating that this model, as simple as this model is, just a bunch of binary variables that say that 2 liquid-like cells like to be near each other, that is sufficient to describe the complex fluctuations of a fluid near its critical point. Okay, so if we were to do those numerical calculations and trace out the phase diagram for the lattice gas, what we would find in the temperature, the useful scale for temperature would be to multiply it by KB, that gives it units of energy, and divide by epsilon. Epsilon's the energy scale in the system. So then that sets a dimensionless temperature. In the dimensionless temperature density plane, that's the average occupancy that is unitless as well. I've already remarked that the critical density is at 1/2. Turns out that in these units, KB Tc over epsilon, where the critical temperature is about 0.58. 1 over 0.58, which is about 2.26. So if I was to draw the phase diagram, oh, that's not very good. It would look something like that, with that critical point at 1/2 and a temperature of 2.26. So underneath here, underneath this region of coexistence, we would find a region of filled cells with a region of vapor-like or sparse filled cells. At high density, the lattice would be completely full. At low density, it would be very sparsely full. And we can imagine now trying to ask questions like, what would we see on specific paths as we controlled the temperature, say at fixed density? Let's imagine a path like this. Let's imagine we fix the density and a little less than its critical density, and decrease the temperature, moving initially above the critical temperature to somewhere below the critical temperature. What do you imagine we would see on such a path? This is away from TC. Well, let's think about it. What does the state of the system look like at high temperature? So at some temperature much, much greater than TC, what does that system look like? What TC demarks where the liquid and vapor are not distinguishable. So at much higher temperatures, we would expect to see some uniform system where locally liquid-like regions and locally vapor-like regions interconvert, producing something which is on average whatever density we've set. We wouldn't see something completely static. There are still fluctuations. The state of the occupancy variables can change over time. But on average, the likelihood that any one cell is filled or empty should be the same independent of where it is in the system. Now, what about if we decrease the temperature a little bit? So we start up here, and now we get to lower temperature. What's going to change? Well, there are still going to be liquid-like regions, molecules up in the vapor that are, although uniform, still going to be attractive. At really high temperatures, thermal energies will break any of those attractive interactions, leading entropy to dominate, things becoming homogeneous. As I start to decrease the temperature, the molecules are going to feel each other a little more strongly. So you should expect that locally liquid-like regions to begin to cluster. Now, they're not going to cluster for long times or for large scales, but there will be some growing characteristic size. And indeed, if I continue to cool below the coexistence line, what should we expect to see then? If I actually go below the coexistence curve, say, end up there, well, there I should start to see phase separation. I should start to see the system know that it likes to have one density, which is vapor-like over large ranges, and one density which is liquid-like over large ranges. So I should see the formation of domains or droplets, such that that characteristic size gets large, so large that it would span whatever container I would see. I would see the liquid begin to condense onto the size of the beaker. Right? So let's actually do that experiment. Let's take that simulation, study a path that begins above the critical point, where the system is uniform, molecules are dispersed, entropy is dominating, and let's begin to cool the system down. Molecules will start feeling favorable attractions more strongly, and eventually I'll cool below the coexistence curve such that I should actually start to see domains form, droplets forming that will span the whole system. Let's do that. Okay, so here's that same simulation I showed you last time. I've started at a temperature of 5, which is much above the critical temperature. And if I start that simulation if you look at any region in space, the system is homogeneous. Any region in space is equally likely to be vapor-like, which is yellow, or liquid-like, which is blue. And the most common size of a cluster, while there are clusters that could be larger than, say, 1 pixel, the most common one is 1 pixel. If I pause this, looked over this system, well, there are a couple aggregates that are, say, 4 or 5 in size. There are a couple that are 2 in size, but the majority, the most probable, is just a single isolated pixel of blue. So now let's cool the temperature down a little bit. Not so cold as to be below the critical temperature, below the coexistence curve, but low enough that interparticle interactions should become more favorable. I should start seeing slightly larger clusters form. And I think you should see that. Right? If I go to back to higher temperature, go back to lower temperature, larger clusters can be seen. They persist over slightly longer times. You can kind of note that that's happening because there's much more yellow space between clusters than there were before, meaning that the particles that were filling those space at higher temperature have now glommed on or aggregated into slightly larger clusters. So now, let's cool the temperature below its critical temperature, where we should expect that thermodynamic equilibrium would mean that the system would phase separate into a single domain of liquid and a single domain of vapor. Now look at that. We very quickly form big clusters, and over slightly longer timescales, the small clusters that are there start to disappear. That medium-sized cluster that was in the middle a second ago is completely gone. This is using periodic boundary conditions like we did when we studied hard disks. Those periodic boundary conditions actually mean that there is only actually one cluster in this whole system, one droplet that just happens to be over in the corner that then is periodically replicated to all the other corners. Let's see what happens if we do that experiment again. Let's go back to higher temperature. Pause it, and we'll quench down to lower temperature where we should see phase separation. Again, very quickly we see big droplets form, and over slightly longer timescales, there should only be one big droplet left, all the other droplets eventually coarsening, that's the fancy word for these dynamics, into that one big droplet. If we cool the system down a little bit more, we'll encourage that to happen. Indeed, we've left with just one droplet that spans a periodic boundary condition. The one in the bottom right is getting shrunken, eventually coarsening, aggregating into that one big one that's just slightly off center. So there's our one liquid droplet in a sea of vapor. If I cool the system down even further, the likelihood that I have a liquid-like cell in the vapor becomes increasingly small. There are very few blue pixels in the yellow region. There are very few yellow pixels in the liquid droplet. If I go to even colder temperatures, the likelihood of seeing a blue pixel, a vapor-like particle, evaporate in, a liquid-like particle evaporate into the vapor is very, very small. Now, why does it form such a compact shape? Well, we discussed that also before when we talked about how liquids convert into vapors or vice versa. Below the critical point, there's a surface tension. That surface tension is free energetically unfavorable. A system will like to minimize the surface area between two unlike phases. And the smallest surface area for a two-dimensional object is to form a circle. And that's why we see the droplet we see here. Okay, let's go back to our phase diagram. So again, we just took this path in red. Let's imagine taking a different path. If we have our phase diagram in the temperature density plane again, where density is the average occupancy of a given cell. It has a critical point at 1/2. Underneath that line is the coexistence curve. Ends at a critical point at some temperature Tc, which we said when we multiply by Kb and divide by epsilon is about 2.26. Now let's imagine a path which actually goes directly through the critical point. So we keep a constant density of 1/2. We start at some high temperature and work our way lower in temperature. And we can actually imagine doing that in both directions. We could march our way down in temperature, or we could take a system in coexistence and go up towards the critical point in temperature as well. So what would we expect to see here? And how would that be different from, say, beginning in coexistence and increasing the temperature towards the critical point? Well, for temperatures above the critical point, whether or not we're exactly on the critical density line or off of it, the sort of behavior should be similar. We should see transient clusters form. And dissolve. As we get towards the critical temperature, the size of those clusters should increase. If we approach that from above. So we should see what starts as a homogeneous phase begin to cluster, and those clusters grow. What about if we start below the critical temperature? So below the critical temperature, we should see coexistence, which would imply an interface between the liquid and the vapor. Now, what happens as we approach the critical temperature from below? So we have an interface that separates the liquid and the vapor. And what happens to that interface? The size of the interface should increase. Because the surface tension goes to 0 at the critical temperature. So we should see the interface begin to fluctuate wildly, bending and contorting with very little free energy penalty to do so. Now, what about exactly at the critical temperature? What happens there? So let's remember our heat capacity experiment. The heat capacity diverges at the critical temperature. The size of fluctuations diverge. They get infinitely large. That means that there is no characteristic scale for fluctuations. They happen on all scales. That means that if I view that system on any length scale, if I viewed a small system at the critical temperature, or a large system, or an even larger system, the fact that the fluctuations diverge tells you that if I looked at the system on at any size, all the patterns that I would see would be the same. There's a specific mathematical term for such a state. Patterns that are self-similar that have no inherent length scale, those are known as fractals. Indeed, a system exactly at its critical point is a fractal. It has self-similar scaling behavior. It looks the same when viewed on macroscopic scales as it does on large microscopic scales. Okay, so let's do those experiments first with the Ising model and see what we see there. So let's restart this at the critical density, which is half blue and half yellow. If we start this from above, so that's at high temperature, there's a high density, so there's a high probability of forming clusters, but those clusters are transient. If I look at one point in space, I'm equally likely to see that space be blue or yellow. And as I start to decrease that temperature, high temperature or slightly lower temperature, you should be able to convince yourself that the size of those clusters do indeed grow. They are still transient, they grow in and dissolve, but their characteristic scale, their characteristic size is larger at these low temperatures than it is at the high temperature. High temperature, low temperature. Okay, let's start below the critical temperature. So at very low temperatures, nothing really happens. I have a perfectly flat interface. That is because the interfacial tension is large. As I start to increase the system, increase the temperature, well, fluctuations begin to occur. The surface tension decreases a little bit, it's still finite. And as a consequence, you start to see fluctuations about that interface. You also start to see transient vapor-like regions in the liquid and transient liquid-like regions in the vapor. Now, as I increase the temperature even larger, the size of interfacial fluctuations are clearly increased. I have larger excursions of the interface into the vapor, and the vapor into the interface, into the interface of the liquid. If I increase that even more, that interface is incredibly rough. It's even hard to say that there's a single interface there by eye. If you wait long enough, you'll see that that interface does fluctuate around some constant average value. Now let's go exactly to the critical temperature. That interface completely goes away. There's no single one long-lived domain anymore. There are big domains that form and disappear. There are fluctuations and clusters that exist on all sizes. This is clearer to see if we look at a slightly larger system. Those fluctuations now have small transient single pixels, larger aggregates, an even larger aggregate that takes a very long time to equilibrate. Whoops. Actually takes quite a long time to equilibrate. That's a very generic feature of phase transitions, that the time scales associated with phase transitions are similarly long, just like the length scales over which their fluctuations are correlated. In fact, I think this simulation is not sufficiently fast to even show you what the equilibrated structure of the Ising model is at the critical temperature, but I have found some simulations, and you could play with this your own, by yourself. If you had some more patience, see that those fluctuations really become on all scales. But a very convincing way to demonstrate that the system is actually fractal is to simulate it, equilibrate it over long time scales for very large systems, and play a little game, which is to ask, if I showed you systems that are really very large, but all at the critical temperature, if the length scale over which fluctuations are correlated really does diverge, they really do look fractal and therefore self-similar, you shouldn't be able to tell the difference by eye of looking at one size system or another. And so this was a little video that Doug Ashton made. Let's see if I can play it here. So there are 4 different size Ising lattices. Black is locally liquid-like, white is locally vapor-like, and I can shrink them into one another exactly at the critical temperature because there are correlations that exist on all length scales. There are regions that look like systems of completely different sizes, which is true independent of what the lattice size actually is. So that self-similarity, I think, is pretty cool. So let's see that one more time. Here again, 4 different sized Ising model lattices can be superimposed on top of each other because there is no characteristic scale of fluctuations. Domains on all scales are represented. So that is then very peculiar. If it really is true that fluctuations are infinite in size, that should actually mean that they're observable to the naked eye. We could see things that exist on a certain scale, millimeters or so, just by eye. And if what I'm saying is really true, that fluctuations have no characteristic scale, then they should have components which are millimeters in size too. And indeed, that's the case. Now, usually in class, I would do a little demonstration with cyclohexene and aniline, which are 2 organic compounds, which has a critical temperature that happens to be close to room temperature, so it's easy to do a little demonstration on. But lacking our talented demonstrators and the equipment in my house, what I have been able to find is a really convincing YouTube video, which has done that same experiment, but for CO2. So CO2 has a critical temperature near ambient conditions, but slightly elevated pressures. So it's not easy to do this in your own home, but experimentalists have made a nice YouTube video to show this. So if I pull this up. So here's the CO2 phase diagram. In the temperature density plane, the critical temperature turns out to be about 31 degrees Celsius. The critical density is quite small, but that's because it's closer to the gas than it is to the liquid. And so what I can show you is a movie which takes two different paths, a path that goes directly through the critical temperature, where you should expect to see fluctuations that occur on all scales, and a fluctuation at constant density that's slightly higher, which really demonstrates that something fundamentally different happens. You don't have that diverging length scale, which is observable even macroscopically by eye. So let me play this little YouTube video. So this is the one starting at the critical density. There's liquid at the bottom, vapor on top. They're going to increase the temperature. You start to see boiling as there's an opacity that starts to develop in the liquid. And eventually they reach the supercritical state. They go above the critical temperature where the interface between the liquid and the vapor has disappeared. So now you can't distinguish the liquid from the vapor. It's at too high of a temperature. It's a supercritical mixture. Now what they'll do is they'll cool it down. And so they'll approach the critical point from above and it just hit it. Look at that. The whole system has gone opaque. That means it's scattering light on nanometer, hundreds of nanometer length scales. That opacity is manifesting density fluctuations that exist on those large scales. Now you see the turbulence associated with an interface that has essentially no tension, that can fluctuate as wildly as it wants to as it starts condensing the vapor into the bottom. As they continue to decrease the temperature, they then form a liquid vapor interface that's well defined. So now this is another example at a slightly higher density where they'll increase the temperature. The interface will eventually go away because they'll go past the coexistence region, forming one continuous supercritical phase. That happens right about now-ish. Nope, still at coexistence. Go to slightly higher temperature. Now the interface has gone away. So this is a supercritical state. But as they cool this back down, because they're not at the critical density, they're at a higher density, the system won't actually proceed through the critical point. You won't see that opacity, that enormous scale of fluctuations of the interface. So you do see the system condense, but that interface forms, well, you still do see some opacity, some turbulence, but the interface stays pretty sharp, even though there are lots of fluctuations. Oh, sorry, this is the point where there's a higher density. This density is so high that they don't actually see supercritical behavior. They don't pass through the critical point. So they'll go to the supercritical state. That interface just continuously changes. It doesn't diverge in scale because the system doesn't pass through the critical temperature, doesn't go through a divergent, doesn't undergo divergent fluctuations. Now as they cool the system back down from that supercritical state, the dynamics is much less dramatic. You'll eventually just start to see that interface grow back in. Now there it is. And it stays pretty sharp at all times, just manifesting the fact that the coexistence densities are changing as they continue to decrease the temperature. So I think that's pretty cool. You can go to that YouTube video link to watch it yourself. The salient physics that underlies that cloudiness, again, is the divergence of the length scale associated with density fluctuations that gets on such a large length scale that it scatters light. So that's hundreds of nanometers, thousands of times the scale of the individual CO2 molecules. Okay, well, that's all I really wanted to say. That's really all we have to say about phase transitions. We're going to continue on in the next couple lectures to discuss mass equilibrium, but in slightly other contexts, in contexts associated with solvation. Yeah, so have a great rest of your day, and I will catch you all on Friday.